This example asks us to find the absolute maximum and absolute minimum values of the function f of t equals the cube root of t times 8 minus t on the interval from 0 to 8. So first we want to consider whether we expect to be able to find such things, because, for example, a function that has a vertical asymptote will not have the appropriate extremum. So we look at this function to consider whether it is continuous or if it has any discontinuities. And looking at the form of this, it is continuous. If there were some discontinuities, then we would want to check whether those are in this interval, because if it had, for instance, a vertical asymptote, but that was outside of the interval in question, that wouldn't matter. As long as it's continuous on the interval we're concerned with, then we do expect to find extrema so long as the hypotheses of the extreme value theorem are satisfied, namely that the interval is closed and bounded, right? So there are two things to consider. One is the continuity of the function on the interval. The other is the nature of the interval itself. This is what we call a bounded interval. It is finite in extent. Neither end wanders off to infinity. And it's also closed, meaning that it includes the endpoints. So we have a closed bounded interval and a function continuous on that interval. So the extreme value theorem guarantees that we have absolute maximum and minimum values somewhere on that interval. To find those, we need only consider the values the function takes on at the endpoints of the interval and also at any critical numbers within that interval. Any extrema of the function have to either be at those ends or at a local extremum, and local extrema can only occur when the first derivative is either 0 or undefined. If you think about this graphically, you would expect if you have, say, a local maximum, for instance, you either have a horizontal tangent line where it changes direction, or you have some sort of corner or cusp or something else where the derivative is undefined. So we'll need to take our first derivative here. We could do this directly and apply the product rule, and that works fine. But in this case, this quantity here is only to the first power. If we had another power, it would probably be a good idea to use product rule. But this is very easy to distribute. So let me actually just do that. This is 8 times t to the 1/3 power. I'm changing the cube root to a 1/3 to make the derivative easier. Minus, we have t to the 1/3 times t to the first. That is t to the 4/3 power. So we have our a different expression for f of t. And again, I did this simply to make the derivative a little bit easier to compute. We'll take f prime of t, and using the power rule there, we have 8/3 t to the negative 2/3 minus 4/3 t to the 1/3. So we need to ask ourselves where this is either 0 or undefined. I like to try to remember to check whether it's undefined first, because that's usually a much easier question to answer than solving to find out where it's 0. And if we do the algebra of finding where it's 0, it's easy to forget that, oh wait, we're supposed to check also where it's undefined. So let's take a look at this. This 4/3 t to the 1/3 is defined and continuous everywhere. There are no problems there. But this t to the negative 2/3, that negative power indicates a reciprocal. And that tells us that we could have possible division by 0. We don't want t to equal 0, right? So there is a critical number at 0. Now, for solving this, we have a couple of options. What I would prefer to do here is to simply say, all right, we can set this thing equal to 0. And let's go ahead and factor out common factors of things that we see. There's a 4/3 in both terms. And the lowest power of t is t to the negative 2/3. So if we factor that out, we are left with 2 in the first term. And it looks like t in the second term. So we have this here. Now this t to the negative 2/3 we know won't be 0. The only way it conceivably be so as if t were 0, but that's actually division by 0. That doesn't do anything for us there. So then the only solution of this equation is when t equals 2. So that gives us our other critical number. If you're less comfortable working with the algebra of these, of these fractions here, the inverse, negative exponents with fractions, all that kind of business, you could, of course, rearrange this. This is 4 times 2 minus t divided by 3 times t to the 2/3. That might be a little bit easier for you to think about and more easily recognize, oh, this is division by 0. Same sort of thing up here. This first equation you could have written as something like 8 over 3 times t to the 2/3 minus 4t to the 1/3 over 3 equals 0. And then if you wanted to simplify this a bit, you could say, oh, there's a t to the 2/3 missing. Let's multiply numerator and denominator here. Then we can combine this as a single fraction. And you'll get something equivalent to this. So there are several ways you could do the algebra, whatever is easiest for you to recognize where the derivative is undefined and where the derivative is equal to 0. Those are the two things you're looking for. So we have these two critical numbers, 0 and 2. And that tells us all of the points where we could conceivably have extrema. Now it turns out that 0 is already one of the endpoints, so we would have been testing 0 anyway. If this had started at a lower value, maybe we're going from -2 to 8, well, this analysis would have turned up 0 as something to consider. Right? So we do need to make sure to look at such things. On the other hand, if this interval were starting higher, like from 1 to 8, then this 0 wouldn't matter because it's outside the interval and we would be able to discard it. But of course, we don't know for sure until we find the critical numbers and then figure out if they matter or not. So we need to evaluate our function at 0, 2, and 8. I'm running out of space. Let's see if I can fit that all onto there. So f of 0, we have the cube root of 0 times 8 minus 0. That is going to be 0 times 8, which equals 0. Now we have 2 and 8. So we have f of 2 and f of 8. Now that I've copied enough of this, I can see where to plug those in. We have the cube root of 2 times 8 minus 2. 8 minus 2 is 6, and we have the cube root of 2 there. That doesn't simplify, that will be irrational, so we have 6 times the cube root of 2. And then for 8, we get the cube root of 8 times 8 minus 8. Cube root of 8 is 2, but 8 minus 8 is 0, so this again gives us 0. These are all of the points worth checking. They're the two endpoints of the interval, and also the critical numbers of the function. And we just evaluated the function there, and these are all of those possible values. So this tells us that the absolute minimum is the least value we see, that is 0, and the absolute maximum is the greatest number we see, that is 6 times the cube root of 2. So this would be our answer here. We do want to be careful with the nomenclature. You might have heard a slight hesitation after I mentioned the critical numbers of f. I was deciding whether to mention this then or now. The common source of possible confusion is when students talk about the critical numbers of f prime. But that is not usually what is meant. The critical numbers of f are values of the variable where the derivative is either 0 or undefined. These numbers are not necessarily critical numbers of f prime. Critical numbers of f prime would be numbers where its derivative, f double prime, is either 0 or undefined, right? So we do want to be a little bit careful here. The critical numbers, we use the first derivative to find the critical numbers, but those critical numbers don't really belong to the first derivative. Those critical numbers belong to the original function. That's how we sort of talk about those things. But that's the idea. It's pretty much all there is to most of the questions in this section. Some of them have slightly easier algebra, many of them have more challenging algebra, but that's really just a question of, how hard it is to find, to solve the equation when you set that equal to 0. That's the chief source of difficulty here. But most of your problems are going to be based on these same ideas here. We want to find critical numbers of the original function. To do that, take the first derivative, find where it's 0 or undefined. And those critical numbers, together with the endpoints of the interval, give you all of the candidate values, assuming that this satisfies the conditions of the extreme value theorem. We want a function that is continuous on a closed bounded interval. Under those conditions, we can be guaranteed to be able to find maximum and minimum values. Pay close attention to whether it asks you for the values or the locations. In this case, it just asked for values. So that was why our answers were just these numbers, 0 and 6 times the cube root of 2. Other times I might ask you for the points, in which case you might need like x, y, or in this case t, y, ordered pairs, that kind of thing. So read the instructions carefully, but those are probably about the only curveballs they might possibly throw at you.